What's up, good people? This is section 2.7, Optimization with Linear Programming. These are mathematics that were developed by the United States Army back in World War II, I believe. And they had a lot. The United States Army is very good at moving things from point A to point B and figuring out exactly the best way to do it. They're they are top in the world at this kind of thing, and became incredibly important in World War II when they're trying to figure out how much food should they put in the ship, how many people, how many tanks, how much supplies, because a ship can only hold so much, and so all of these things have a cost, all of these things have a weight, and so it's not exactly, you might not exactly be sure how many what way to do it. And it's called linear programming because eventually what they ended up doing was writing all these inequalities and equations, putting them into computers and letting the computer spit out the answer, or the best possible answer. This is actually based on section 2.6 a lot, so most of the work we're going to be doing is going to be from the previous lesson, the previous video. But let's get some vocabulary first. So a constraint is a real-world limitation represented by an inequality. And we've been graphing inequalities, and so we're going to use what we learned last class. The feasible region is the intersection of those constraints. Oh, wait a minute, we've been intersecting inequalities, and so that's exactly what we're going to do. Feasible region is going to be all the different points that satisfy all the inequalities at the same time. Their intersection of those constraints, those inequalities. And the optimal value is going to be the best point in a feasible region and will often be one of the intersection corners. Best, how do you know what best is? Often by price, like it's the cheapest, or maybe it's the highest profit, the highest amount of money. Let me show you what I mean. This is not exactly the army, but this is Juan making pottery. He's got 8 days to make pots and plates to sell at a local craft fair, and he's going to make some money on that. Each pot weighs 2 pounds and each plate weighs 1 pound. Juan might be a beefy guy, but he can't carry more than 50 pounds to the fair. Each day he can take at most 5 plates and 3 pots. He will make $12 profit for every plate and $10 profit for every pot that he sells. So what's its maximum profit and how should he achieve it? There's lots of combinations of pots and plates that he could make, but he wants to know how to max out that bling. So let's figure it out. Knowns and unknowns. We're starting this exactly the way we would in section 2.6. We've got knowns and unknowns. What don't we know? We don't know how many pots and how many plates. So let's make those our unknowns. Those are X and Y. I'm choosing X. It could choose like different letters, but I'm choosing X and Y because I'm going to be graphing them pretty soon. Well, what do we do now? We've got a total of 50 pounds, and you can't go over that. Total weight is 50 pounds. So then things are going to add up, and they should be less than or equal to 50 because 50 is the max. Also, he's got 8 days, and he's got this kiln that he can make at most 5 plates and 3 pots every day. Like that's just what the kiln can handle when he fires it up. That's how much space he has. He's got a constraint. He's got a constraint on the weight, 50 pounds. He's got a constraint at 8 days, 5 plates. 5 pots a day. That's 8 times 5 is 40. And then he could only make 3 plates. 3 plates times 8 days is 24. So he's got a max of 40 of these and a max of 24 of these. All right. Also, we know that they weigh 2 pounds. Pots, 2 pounds each. Y, 1 pound each. Then here's the new. All that was should at least be a little familiar from the last video in the last section. But here's the new thing. Profit. This is an equation that has 3 unknowns. We don't know the profit. We don't know how many X. We don't know how many Y. But this is how we're going to calculate the profit. We take whatever X value, however many pots we choose, that'll be times 10 plus however many plates we choose times 12 and add them up, and that's the total profit. This is the equation that's going to help us figure out which point in the feasible region is actually going to be best, because we want to maximize that profit and be rolling in the money. Here we go. Taking this red known, the total weight, we can turn it into an inequality. This is the red constraints turns into 2x plus y is less than or equal to 50. Good. Now we're going to have to graph that, so I'm going to solve this for y. I'm going to choose to solve it for y, and you can see I'm graphing y equals 50 minus 2x. I'm choosing 0 to be 0, y equals 50 minus 2 times 0 is 50. I could also choose 0 here and back calculate 25. In fact, maybe I'll do that right now. Can I change that? Yeah. This is going to be 0. I'm going to choose 0, and then I'm going to back calculate. I like that better. 0 is equal to 50 minus 2x. We don't know what x is, but you can see we add 2x to both sides, divide by 2, we got 25. Good. So we got two different, you can see I'm graphing this, I got an equation, table, and now I'm graphing the line, boom. So 0, 50 and 25, 0 are the x and y intercepts for this red line, making it solid because this is a less than or equal to symbol. I don't think we need tables for the blue inequality or the gold inequality because they're just x is equal to 40 is this line right here, and y is equal to 24 is this line right here. We've got to figure out which region to shade because each of these lines divides the plane in half into two different portions of the region. But 0, 0 actually is a point that satisfies all three of these inequalities. It satisfies this one. You put in 0 for x, ding. Put in 0 for y, ding. Put in 0 and x, 0 for x and y here, and you get ding. So 0, 0, 0 is actually a really popular place. It gets shaded all three times. This is the region right here that gets shaded all three times from these three different inequalities. And so, based on these constraints, Juan could just sit on his butt for the next 8 days and not make any plates and not make any pots and skip the craft fair and just watch Netflix at home and make no money. That is actually one possibility, but he ain't gonna do that because he's a go-getter. That's not going to be the optimized. That's not going to be the optimal value because you can see we want to make some money. What we got to do here is the best pot, the point that is going to make the most money is most likely going to be one of these corners. So it's incredibly important to figure out where the corners are. 0, 0, easy to figure out. Here it is, 0, 0. This one over here, I've already figured out this x-intercept is 25, 0. I put it in a table over here. This is new. We didn't have to do this before. Here, I should also say that there's no way Juan's going to make any decimal number of plates. Like he can't make 2.5 plates, and he certainly can't make a negative number of plates. So all negative numbers are off when it comes to this kind of thing. If you cut off the negative numbers, then it's left with this trapezoid right here in black. And the corners are what we're finding of this trapezoid. This point is kind of easy to find because if I remember, this is 0, something, and the height of this gold line is 24. Y equals 24 is the equation right here. So 0, 24 is this other point right here. And the hardest one to think about is what is this point right here. We know that it's going to have a height of 24, a y value of 24, so you can plug that into the red equation right here. And if y is equal to 24, we can back calculate that x would be 13. I didn't show that work. I'm just going to keep on moving on. So that might be the newest. Oh gosh, maybe I should do it. All right, check this out. Do it right now. So we know that the y value is 24 because it's on the gold line. So 24, and then that means if the y is 24, then we get 24 is equal to 50 minus 2x. Boom. And we've got to figure out what x is. Solve that equation, you get x is equal to 13. Okay, now I showed a little bit of work to see how we got that. 13, 24 is the last corner. And so you can see here, this is a table that shows all the x and y values of all the corners, all these points that are plotted to make up the trapezoid. Which of them is going to be best? Well, we could go full throttle on plates and just say that like y could be a high y value of 24. That would be okay. 0, 24. Why did I say 0, 24? That should be, oh yeah, it's up here. You could go full throttle on plates and go 0, 24, boom. And that would make some money. It would make $288. How do we know? Because we're using this profit equation right here, 10x plus 12y. And that's what I'm doing over here. 10x plus 12y is helping you calculate all the profit. 0x, like 10 times 0 plus 12 times 0 is going to give you a 0 profit, so that's really not going to make him any money. You could go full throttle on pots. 25 pots is the max, based on how much he can carry. Like he hits that constraint right there. It can't go any higher than 25. So you could load up his backpack with just 25 pots, and that'll make him $250 based on the profit equation. And then, but actually, the most amount of money is to go some of each, like a little bit of some pots and some plates. X could be 13. X is, I keep on referring to my knowns and unknowns. That's why it's so important. X is pots. 13. 13 pots and 24 plates would give him the most amount of money, $418. And that's this is the answer. When you've analyzed each corner based on a profit equation, and you find out what's the optimal value, then the answer is 13 pots, 24 plates for $418. Boom, done. I wanted to say right now that we're going to do some zoo food. Example 2, zoo food. The zoo is mixing 2 types of food for the animals. Each serving is required to have at least, that sounds like an inequality, a total of 60 grams protein and 30 grams of fat. Custom Foods has 15 grams of protein and 10 grams of fat. Cost that amount. Zookeeper's Best contains this amount of protein, this amount of fat, and this price. So, what food should be prepared to minimize the costs? Minimize costs. That means we want to make sure our third equation, the one that helps us find the optimal value, is going to be money. What we don't know is how much of Custom Foods and how much of Zookeeper's Best. Let's label them X and Y, choosing the letters from the alphabet that we're going to be graphing. Knowns. Okay, what do we know? We know we've got to have at least 60. You can have more protein. Animals, we love our protein. So we need to get at least 60 grams of protein. We need to get at least 30 grams of fat also. Yeah, so more than that is actually fine. Great. So total protein, that's 15x plus 20y, has got to be greater than or equal to 60. Total fat, 10x plus 5y, has got to be greater than or equal to 30. Might as well test to see if 0, 0 are solutions to these inequalities, and they actually are not to neither of them. So 0, 0 is not going to get shaded when we graph these suckers. Here we go. 15x plus 20y is equal to 60. That's the equation version of this red inequality, and we're just going to do this. Plug in 0 for x, solve for y. Plug in 0 for y, solve for x. There's to give the x and y intercepts. You can see I've graphed them right here. Plug in 0 for x in the blue, and calculate y. Let's plug in 0 for y, and I bet you could calculate what x is right here. And so I've graphed these, both of these red and blue lines, and you can see 0, 0 is not a point that is allowed on either. So there it is. We've got 0, 0, and it doesn't get shaded. The other halves of the region gets shaded, and this region actually gets shaded twice. So here we've got these lines, and actually we've got 2 types of foods. So what food should be prepared to minimize costs? It doesn't look like we're allowed to actually even... Oh, these comes in units. Right, so you can't buy half of a unit. You can't buy a third of a unit or a decimal amount of units in these. It's like canned food. You can't buy half a can of whatever custom food. We're only looking for, and you can't buy negative ones either. So we're looking for whole number answers. Like here, this intersection right here, maybe this corner right here would actually be an optimal value, 2.4 cans and 1.2 cans of food. But you can't buy 2.4 cans of food and 1.2 units of food. That'll give you it's just impossible. So what we've got to do is we've got to look around this feasible region. We're going to try a whole bunch of them, and I'll show you on your calculator how to do this a bit more easily. The intersection point is here. That's actually the cheapest thing to do, like 2.4 cans, and 1.2 cans over here. But you can't do it because we've got this. So So I'm choosing different points along this feasible region, and they're all plotted here. And you can see the cheapest one is actually to go 1 and 4, 1 can of custom foods and 4 cans of Zookeeper's Best, and that would only cost you $2.80. That's pretty cheap. There, that's the answer. Let me show you what this looks like on the Inspire. This is not a word problem. You can actually type these in to your Inspire, and actually, this is a screenshot of my Inspire, what it looks like. Let me show you right now. I'm going to jump to the Inspire. Boom, boom, boom. There it is. All right. So you can go to the graph, and you can type in, you delete the equal sign and type in a relation. So now we're actually going to be typing in those equations that you see in your packet. We're going to go X, and then Control equals brings up the menu. X is less than or equal to 4. Boom. Let's go tab again. Relation number 2 is going to be X, and then Control equals brings up the menu. I want to go use the right arrows to, the down arrow to get to that greater than or equal to symbol and type in -2. And there it is. Whoa, shading. It already knows. It does it automatically. Isn't that awesome? Let's type in a third relation. Y is equal to, no, not equal to, we do Control equal button, and then less than or equal to, what's it going to be? X plus 2. Type that in. Boom. Shaded. Tab, relation 4. Y, Control equals to bring up the menu. Use the arrows to cycle through. Greater than or equal to -0.5 x minus 3. Enter. Wow, we've got all 4 lines graphed, and the portion that gets shaded most. Oh, we have to find the intersection. So we've got this feasible region, and it's all in the middle. So we have to find out where the intersections are. You can do that using a trace. Here's where it's really important to only use left or right, because if you use up or down, you're cycling back and forth between equations. So go left, go right, and find the, oh, you can't even see it because my head's in the way. You can find the actual locations, the intersection points right there. Now maybe you want to use intersection tool, but I'm just using trace right now to go back and forth. Maybe a better way to do this would be to jump onto the blue line. Now we can go press the left and right arrows, not up or down. We go 4 comma something would give us that value. And then go back and forth. You can find that the x value here is -2 on that intersection. All right. We're going to keep going, and we're going to go to the menu. And now that I've written down in my packet all the different parts, we're going to go menu. Yeah, let's delete everything because we're all done. We found the intersection points and we've written them down on our packets. Menu 1, that was menu 1 action, and then delete all. We're going to put them back to 3 graph entry edit function because that's what we normally use. Now that we've reset our calculator and we found our intersection points of the trapezoid, we're going to go to new, add calculator, no, add list and spreadsheet. That's the 4th option. This looks like a Google Sheet or an Excel spreadsheet. And what I'm going to do is I'm going to type in all of the intersection points that we found. 4, 5 was the first intersection. -2, I can use the tab button if I want to get to the next cell. -2, -2 is the next intersection. Using the arrows to go -2, tab. Oh wait, not -2. Yeah, -2. Come on, Bergman. Negative 2 comma 0 was the next intersection point, the next corner of the feasible region. And 4 comma 6 was the next corner of the feasible. These are x and y coordinates of all the different corners of the feasible region, the region that got shaded all times. Now this third column is going to be the equation that helps optimize everything. So we're looking for negative 2, and then I'm going to type, check this out, I'm going to type an A, and that A refers to the A column, plus 6 times B. That B refers to the B column. And if you do it right in that upper gray square, then it's going to give you, when you press enter, it's going to give you a list of values. And I want you to try and figure out what is the optimal value. In the case, the video's over. In the case of this, we're looking for the highest value that this function. You put in all 4 corners, you get an x, you put in the coordinates of x and y for each of the 4 corners, and you should get, I want you to tell me what the highest number is. And that's your Inspire for today. Take care, and I will see you tomorrow.